All right, let's jump right in. We're going to tackle a huge question in the world of software today. How do you build these incredibly complex modern systems that, well, just don't break? We're going to dive into the core principles of architecting for resilience.
So let's kick things off with a big what if. Just picture it for a second. What if that system you use every single day, or the one you work on, could just run forever without a single hiccup?
Yeah, the hard truth? It can't. That's just reality. Hardware fails, networks get weird, and hey, software has bugs. So the best engineers out there, they don't even try to prevent failure. Instead, they plan for it. They design for it.
And that right there, that's our first big idea. This is all about a major shift in how you think. It's about accepting that failure isn't just some possibility. It's an absolute certainty.
This quote just nails it perfectly. Reliability engineering is about designing for failure, not hoping it won't happen. It's about looking failure straight in the eye and building a system that can take the punch, not just crossing our fingers and hoping for the best.
Okay, so if we're designing for failure, how do we actually do it? Let's move on and look at our first line of defense, the absolute core building blocks you need for a resilient system. Let's get into the nitty-gritty with our first key term, the single point of failure, or SPOF. The best way to think about this is like a chain. A SPOF is that one single weak link. If it snaps, the whole chain is useless. It's that one piece that can take everything else down with it.
And this slide just lays it out perfectly, right? On the left, you've got this really fragile design, one server. If that goes down, game over. The system is offline. But look at the right. A load balancer is spreading the work across a bunch of servers. If one of them fails, it's no big deal. The others just pick up the slack.
Our next building block is the container. Now, the best analogy for this is to think of it like one of those standardized shipping containers you see on boats, but for software. It packs up your application and absolutely everything it needs to run. All the code, the libraries, the settings, the whole shebang. And the result? The code that works on a developer's laptop, well, it works the exact same way in production. So, why does this matter so much? Well, it gives us 3 huge wins for reliability. First, we can get new code and fixes out the door way faster. Second, we can isolate our services, so one misbehaving service can't mess with another. And third, we can easily spin up more copies, or scale, whenever traffic spikes.
But what happens when one little thing goes wrong and isn't contained? Well, that leads to maybe the most dangerous situation in any complex system. Let's talk about stopping the domino effect and how we can prevent these cascading failures.
It always starts small. Maybe service A fails for some random reason. A bug, a network glitch, doesn't really matter what.
But here's the problem. All the work that was supposed to go to service A, it has to go somewhere else. So it floods service B, which, it was never designed to handle that much stress. So now it fails.
And you can probably guess what happens next. The load shifts again, it hammers service C, and boom. The entire system just collapses. One tiny, isolated problem just caused a total, catastrophic outage. That is a cascading failure.
So how in the world do we stop this from happening? Well, engineers have some really clever tricks up their sleeves. First up, timeouts. Instead of just waiting around forever for a broken service to maybe respond, we just fail fast and move on. Second, circuit breakers. This is just like the fuse box in your house. If a service keeps failing, the circuit trips, and we temporarily stop sending it any more traffic. And third, bulkheads. Think of the watertight compartments on a ship. They isolate resources so a failure in one area doesn't sink the whole boat.
And really, this quote just sums up the whole goal here. You can't always prevent that first little failure, but you absolutely can, and you absolutely must, isolate it. You contain the damage so the rest of the ship stays afloat.
Containing a failure is one thing, but what if the system could actually heal itself? Let's jump to our next section and see how we can build a self-healing system using smart automation and detection. It all starts with something called service discovery. And honestly, the easiest way to think about it is like a GPS for your entire system. See, in a modern setup, services are constantly starting and stopping. Their locations are always changing. Service discovery is like the central directory that always knows exactly where to find the healthy running services at any given moment.
So how does that system GPS know who's healthy and who's not? That's where heartbeats come in. Every single service is constantly sending out this tiny little signal, like a pulse, that just says, hey, I'm alive, I'm okay. If that heartbeat suddenly stops, the system knows immediately that something's wrong, and it stops sending traffic that way. It's basically the system's vital signs monitor.
Okay, but wouldn't it be better to catch problems before a service completely dies? Of course, and that's exactly what anomaly detection is for. This is your early warning system. It's constantly watching key metrics, like how long responses are taking, and if it sees something weird, like a sudden spike, it can alert engineers before it spirals into a real outage.
All right, we've thrown a lot of concepts at you. Let's pull it all together and see what this stuff looks like out there in the real world. This slide is a great summary because it connects the strategy to the direct benefit. Getting rid of SPOFs means you avoid total outages. Using circuit breakers gives you that critical failure isolation. Anomaly detection lets you be proactive. You can see how each piece adds another crucial layer of protection.
And look, this isn't just some abstract theory. You're actually using systems built with these ideas every single day. The cloud platforms we all rely on, they're built on containers and service discovery. E-commerce sites use circuit breakers so a glitch with your credit card doesn't crash the whole checkout process. And streaming services, they use anomaly detection to catch buffering problems before you even notice them.
So, what can you do with all this? What are the big takeaways? Well, here's a simple checklist to get you started. First, go hunt for those single points of failure. Then, make sure your critical services are containerized and you have more than one copy running. Go add some timeouts and circuit breakers. Check that your service discovery and heartbeats are actually working. And finally, get in the habit of reviewing your metrics to spot those weird anomalies early.
And that really leaves us with one final crucial thought. Every single system, no matter how big or complicated, is only as strong as its weakest link. So the real question is, have you found yours? Thanks for joining this explainer.